itself here suggests that we are going to look at vectors of infinite length, right? So for Rn or Cn, what is the length of any vector? Take any vector from Rn or Cn. What is the length of any vector? The number of coordinates only is the length of the vector. So for, let's say you have a vector from Cn, can you tell me what is the length of the vector? Yeah. So the length is n, right? Okay. So now here you see that the vector is not going to end at all. The length of the vector is just going to keep on continuing. It goes to a 100, a 200, a 1000, and it keeps on going. Okay. Such a vector of infinite length, okay, we call it as a sequence. Okay. So what are sequences? Sequences are nothing but vectors of infinite length. Okay, so there is one thing more about something more about these vectors. Like for sequences, you already know from math 1, right? So whatever you, if you know what is the nth term, so if you know what is an, then you can write what is a1, a2, and for all the other vectors you can write what are the entries, right? So if you know an, it is sufficient to write the entire vector. Okay, so the vector addition is usual, the usual coordinate wise addition only, and the scalar multiplication is also, you have to multiply the scalar for all the coordinates. They are the usual addition and scalar multiplication. And what is the zero vector here? So the zero vector here is just the sequence of infinite number of zeros, that's all. Okay, so here you can see that, easily see that this is just the extension of Cn with usual addition and scalar multiplication. So you can verify easily the all the properties of the vector spaces here. So this set is called the sequence space. So what is the sequence space? So the sequence space, how it is defined? It is a set of all vectors of infinite length where you have AI in C. Okay, so collection of all such A. So maybe I'll write collection of all such A's is called the sequence space. Okay, so these can be thought of as vectors. So here you see that now in this case we have considered them as discrete. Here you see that I is varying like 1, 2, 3, 4. So there is gap between 1 and 2, 2 and 3, right? So this is a discrete setting. But you can also consider it as functions. It means what? You can have a continuous domain. Your t, for example, can take a values from some interval. Okay, so you know that these are functions of one variable, and this can also be represented as a vector, right? So suppose you have a function x of t, which is a function of just one variable, and the codomain here x of t belongs to C means what? X of t belongs to C means this is your codomain. So C is your codomain, right? And your t can belong to some interval. Okay, so these are functions of one variable. Okay, so here it is, the variable is t. So how do you add two vectors? Simply x of t plus y of t. And how do you multiply with a scalar? So you just multiply the function with the scalar. So since these are well defined function, the sum as well as the scalar multiplication, they are also well defined. Okay, and what is a zero vector? It is the constant function where all the entries t, all the elements from the domain are mapped to 0. Okay, so you can again check that this satisfies all the properties of a vector space, and this is called function spaces. So the earlier one is sequence space, and this one is function space. So what is your function space? Your function space is nothing but set of all x, or we can even write set of all x from a comma b to c. Okay, so all the functions. Okay, all functions from domain A comma B. Okay, fine. With codomain C. Okay, fine. Now here you see that. So suppose let us say you have the domain 0 comma capital T. Okay, maybe this T is referring to time in signal or something. Okay, so the exact same thing, okay, is defined here. Only thing I have mentioned some domain A comma B. So here the domain is mentioned as, so this is your domain. This is your domain. Okay, the domain is mentioned to you. It means what? Your x is a function from 0 comma capital T to complex space. Okay, so whatever we saw here, the exact same thing is given here for this domain. That's all. Okay, here we considered a general domain and here just 0 to T. Okay, fine. Now we have sequence spaces, we have function spaces. What are we going to do? Okay, so here note that first of all, whenever you are considering sequence in terms of your signals, they are discrete time signals, and x of t means you are considering functions as continuous time signals. Okay, so both are vectors. So this is a vector from the sequence space and this is a vector from the function space. Okay, so whatever vector spaces you are defining, the elements of the vector space we are referring to as vectors only. Okay, whether they are functions, sequence, or just vectors or matrices, whatever it is, if your if your the if whatever element you are considering is from a vector space, then it is a vector. Okay, so here we are going to define then in the next stage what are inner product for such vectors. Okay, we have already seen the notion of inner product for Rn and Cn. So we are going to try to do something similar to sequence spaces and function spaces as well. Okay, so how can we do that? So here let us say you are having two sequences. Okay, and these sequences have entries from R. So you already know if you have finite sequence, like if you have two vectors, how do you define the inner product? So suppose let us say you have x1, x2, xn and y1, y2, yn. What is the usual inner product for real numbers? So it is simply x1, y1 plus x2, y2 plus etc. xn, yn. So the exact same thing only here. Only difference is that instead of just stopping at n, since there are infinite number of entries here, you have to keep on doing this multiplication infinitely. Okay, so this is an infinite series. So what is a series and what is a sequence? Can anyone tell? What is a sequence and what is a series? Anyone? Okay, so sequence means you just have a set of numbers. Okay, so for example you can have a sequence an is equal to 1 by n. Okay, so here maybe you have 1, 1 by 2, 1 by 3, 1 by 4 and so on. Okay, so now this is a sequence, right? Now suppose you, instead of n equal to 1 by n, suppose I am considering 1 plus 1 by 2 plus 1 by 3 plus 1 by 4. Instead of just considering with commas, if I am considering their sum, then this is a series. Okay, so this is an infinite sequence and this is an infinite series. Okay, so this is the difference. So sequence means they are just numbers with separated with comma. Series means you have sum of the numbers. Okay, fine. So here you have the inner product as an infinite series. What is that series? So the series is nothing but summation I is equal to 1 to infinity xi yi. So this is your infinite series. Okay, so remember, so the inner product is well defined only when the series converge. Okay, so the series, the convergence and divergence of sequence and series, please recall it from math 1 if you have forgotten these concepts. Just go back and look at the sequence and series once. Okay, So this inner product is defined only when the sequences, when this infinite series is convergent. Okay, fine. Now this is for real numbers. Suppose you have complex number like this. Okay, so here since we are representing xi yi, so if you put again I here for imaginary, it will be confusing. So instead of I here, we are putting j for the imaginary number. Okay, so here you have xi is equal to ai plus jbi, and yi is equal to ci plus jdi. Okay, so these are two complex numbers. So now how, but remember these are complex numbers, but now when you change this I as 1 2 3 and so on, you are going to have what? So here x is equal to x1 x2 xn and so on. So this is now a sequence. Same way, y is equal to y1 y2 and so on. So this is a sequence. So both are sequences of complex numbers. Okay. So now what is inner product of x comma y? So it is x1 y1 bar plus x2 y2 bar, just like we did for cn, right? So plus xn plus yn bar plus etc. Okay. So here note that what will happen when we are doing this inner product. So you will get both real and imaginary part. Okay. So the real part is here and the imaginary part is here. Okay, so again remember that both the real part and imaginary part. So now you have two series in this case of complex numbers. One is the real part and the other is from the imaginary part. Both this infinite series should converge, then only you can say that this inner product is well defined. So the first series as well as the second series. So what is the first series? Your first series is summation I is equal to 1 to infinity aici plus bidi. Is it correct? Or is it changing? It cannot change, right? X2, Y2. I guess here some error is there because these terms are same. So this some error is here in this line. I guess I will just rewrite this before posting this. So this statement does not look correct. Okay, so this part I'll verify and write the correct one. Okay, verify. Okay, so there are some errors I see. Okay, so but this is nothing but simple complex number multiplication only, so nothing big here. So you can also do this and see what is the correct term here. So you will get two series, one is the real part, the other is the imaginary part, and both should converge so that the inner product is defined. Okay, so now you have the sequence spaces. So this whatever inner product we have seen, this is for sequence spaces, and that space we are giving it as a name, the name small l2. Okay, the name is small l2, and this 2, what does this 2 represent? So this 2 here, it is represented like this: the set of all sequences where xi belongs to c such that the real series. Now you have a real series. What is that real series? Mod x1 squared plus mod x2 squared plus etc. converges to a finite number is defined to be the sequence space L2. See, when we said that when this series is convergent, then only this inner product is defined. Like this we are telling. So instead of saying this condition every time, now we are going to define the sequence space itself in this way. So this sequence space L2 contains only the sequences where this series is convergent. What is this series? This series is nothing but summation I is equal to 1 to infinity modulus of xi square. Okay, only when this series converges, you can say that this particular sequence belong to L2. Okay, so L2 is a set of all sequences such that this series is convergent. Okay, and what is this series? Can when you compare it with the inner product, can anyone compare it and tell me what is the relation between this series and the inner product? So you have the inner product here. How can you relate this inner product with this series? What is the relation? Yeah, it is inner product of x comma x. Good, right? So this is nothing but inner product of x comma x. Okay, fine. So you see that this inner product x comma x is this series, and this, if this series is convergent, it means this is defined, right? Okay, so now here are some examples. Now look at this particular sequence. What is an here? Can anyone tell what is an here for this sequence? What is an? So you have a naught, a1, a2, and so on. So what is your an here? What is your an for this sequence? Yeah, you tell any one of you at least, then we'll continue. You understand my question, or if you don't understand, please ask me. What is the general term for this sequence? For any sequence, you have a general term, right? I'm asking what is that general term. If you don't understand, or if you don't know how to find it, just tell me, or if you keep quiet, then no point of continuing. At least one student, if I know that is attentive, I can proceed. Geometric mean, yeah, see, it is a geometric sequence, that is different. Yeah, but what is the general term? General term is a power n, right? That's all. An is nothing but, so here you have a number a, or if you want to consider it as xn also, that is also fine. So if you want to consider this instead of a, if suppose a is confusing, then you can write it as xn. So this is your x naught, this is your x1, this is your x2. So in general, xn is nothing but a power n for some fixed number a such that modulus of a is less than 1. Now, what do you know about the series for this particular xn? So you know that what is the series corresponding to this? So this particular summation I is equal to 1 to infinity xi square. Okay, so here xn is nothing but a power n. So summation n is equal to 1 to infinity. Here modulus of xn square is nothing but, so xn is what? A power n, right? So you have summation n is equal to 1 to infinity a power n square. Okay, now you have this square of modulus. So you can take out this n. It's not going to do any change because you are having anyway a square here, and also you have modulus, so not, you are not going to lose anything. So you have modulus a whole power 2n. Okay, so this you can write it in this way. Okay, now does anyone remember when this series will converge? When this series will converge? When this will converge? For what values of A this series converges? Yeah. For what values of A this series will converge? No one remembers? Okay. So here this series will converge when you have modulus of A less than 1. Okay, so when modulus of A less than 1, this geometric series will converge. You know that modulus of a squared is also less than 1. So this series is going to converge. Okay. So your sequence a power n will belong to L2. Okay. But if modulus of a is greater than or equal to 1, so when equal to 1, you know that it is just 1 plus 1 plus 1 infinite times. So obviously it diverges. And same way, modulus of a greater than 1 means you see that it is just again going to infinity, right? So this does not belong to L2. So for mod A greater than or equal to 1, this is not going to, this series does not converge. Only for less than 1, it converge. So you see that this sequence belongs to L2 and this sequence does not belong to L2 because here modulus of A is greater than or equal to 1. Okay. And here, what is your xn? Can you tell me? For the second case, what is your xn? So in both these cases, xn is the same, right? It is just a power n. Now for this, what is your xn? For the second example, what is your xn? 1 by n. Good, good. So it is 1 by n, right? So now for this one, what is your xn? The other part, 1 by root n, right? So you see that here you have 1 by n and 1 by root n, right? Now let us consider the series summation n is equal to 1 to infinity modulus of xn square. So you will see that here you have, so this is summation n is equal to 1 to infinity modulus of xn square. So your xn is 1 by n. So you will get simply summation n is equal to 1 to infinity 1 by n square, right? And you know that the p series here will converge because here the p value is strictly greater than 1. Okay, so 1 by n power p will converge only when p is greater than 1, right? So here specifically p is 2, so you know that this series converge. Okay, and in fact this is the sum for this p series. Okay, so this part you know that this is in L2. What about the other part? What about this part? For this you will get summation n is equal to infinity 1 by n, right? It is simply 1 by n. So maybe I'll write here. So summation n is equal to 1 to infinity mod x n square is nothing but summation n is equal to 1 to infinity 1 by n. And you know that this is a p series where p is equal to 1, but p series converges only when p is greater than 1. So this is not convergent. Okay, in general, if you consider the sequence 1 by n power p, then this sequence belongs to L2 when p is greater than 1 by 2. Okay, so here you see that here n is equal to, sorry, p is equal to 1, and here your p is 1 by 2, right? So you see that this sequence belongs to L2 only when p is greater than 1 by 2, and for less than 1 by 2, less than or equal to 1 by 2, the sum of the squares will diverge. So 1 by n per p will not belong to L2. Okay, so this part you all understand the example. Okay, so here you see that now since this series is converging, you can define the inner product, right? Because here you know that the series is now convergent, the inner product is well defined here. And what is the norm of any vector in L2? It is simply the series summation n is equal to 1 to infinity mod xn square. That gives you the norm square of any vector in L2. Okay, fine. So now we will look at the next scenario, right? So now we have seen what are sequence spaces. Now how to do something similar for function spaces. Okay, So for function spaces, it is not very much straightforward, just like we saw in the case of sequence space. You see that it is a simple extension. This definition is a simple extension of whatever the definition we have seen in Rn and Cn. But here for function space, it is slightly different. Okay, so for function space, so suppose you have two different functions like this. Okay, so now here you see that this inner product x comma y is defined like this for function space. Okay, so the inner product x comma y is defined here. You need an 1 by n here. This is important. Okay, so you are taking like now for first at 0 and then at 1 by n and then 2 by n. So each time you are taking an 1 by n interval, and that you are doing a multiplication here. This is how you are defining inner product x comma y for function spaces. Okay, but here you see that you are now again considering a discrete scenario only, but for function space you need a continuous scenario, right? So for continuous scenario means you need something like an integration to have an entire idea of the curve, right? So here for function spaces, first of all, just like we had small L2, here we are now going to have capital L2. How is this function space is defined? So the set of all function x of t from a comma b to c such that this integral. So earlier in place of this integral, what did we have in the discrete case? In the discrete case, we had infinite series, right? Summation n is equal to 1 to infinity mod xn square. Now instead of series, we are going to have integration because you are now in a continuous setting. So you have infinite a to b modulus of x of t whole square dt, right? So if this is a finite real number, then we can define such functions to be L2, capital L2. So what is capital L2? The collection of all function where this integration is defined. So it is a specific real number. Okay, so that is capital L2. Okay, so for example, now what is x of t equal to t in L2? How many of you remember just the usual integration? Let me check. So just compute, everyone take your paper and pen and just check whether you remember integration. Compute integral minus 1 to 1 x of t mod x of t square dt for this function x of t. So here I am specifically giving your x of a comma b to be minus 1 to 1. Compute this and tell me what is the answer. Let me see how many of you are able to remember integration. Everyone try this. Try this and tell me what is the integration. Yeah? Anyone? If you are still doing it, at least let me know that you are doing so that I will wait. Unless you are remembering integration, this part is going to be very difficult. What is the integral? What is the integral value here? 2 by 3.
2 by 3,
Okay,
ma'am.
good, good. Right? So how do we do that? We simply take x of t equal to t means minus 1 to t, minus 1 to 1 mod t square dt. Right? Mod t square is same as t square. So when you do the integration, it becomes t cube by 3, and then you just apply the limit minus 1 to 1. then you will get 2 by 3, right? So this is for x of t equal to t. So it means what, this you got it as a finite number. But if suppose you are taking x of t is equal to 1 by t, just try computing and see where are you having difficulty. So just compute the same for x of t is equal to 1 by t. We will see where you are having difficulty. So one thing I'll tell you before you do this. So is this function defined when t is equal to 0? Is this function defined at t is equal to 0? No, right? So whenever you have finite number of discontinuity, your integration is not affected. So here only one discontinuity here is here. So it's fine. So you can simply split the integration as minus 1 to 0 mod x of t square dt plus 0 to 1 mod x of t dt. Okay. Now you proceed. So whenever there is a discontinuity, you have to split it. So you can do this, just I'm recalling this for you. So as long as you have finite number of discontinuities, you can easily split this integral limits like this and still continue the integration. Okay, when you have finite number of discontinuities. Here only one discontinuity, so you can split it like this. Okay, so do you see that there is some issue with this function? Is this, are you able to calculate the integration for this function? Any one part? Okay, let's see what's happening here. See, now what is integral of minus 1 to 1, 1 by t square, right? So here your x of t is 1 by t. So modulus of x of t whole square is 1 by t square, right? Now we are splitting this integral like this, right? And then you see that what happens to, so here either you take this part or this part, it does not matter. You can take any one part and see what's going on. So here you see that you are now, so at 0 is here, minus 1, 1. Okay, in this part, so if you are doing this integration, it is minus 1 by 2 and the limits are 0 and 1. 1 you don't have any problem, so you simply write. But at 0 it is not defined, so you have to write limit t going to 0 plus. Why it is 0 plus? Because we are on this part, so we are approaching 0 from the positive side, right? So this is 0 plus because we are approaching it from the positive side. Okay, so limit t goes to 0 plus 1 by t. And is this limit defined? Does this limit exist? This limit does not exist, right? So even if one of this is undefined, then this integral does not exist, right? So this integral is not defined. So if this is not defined, then what can we say about this x of t? This x of t does not belong to capital L2. Okay, this x of t does not belong to capital L2. Okay, so do you understand what's going on here? Yeah. So this function belongs to capital L2 and this function does not belong to capital L2. Okay, fine. So here you see that you have sine of 2 pi kt by t, right? So and the interval here is 0 to t, right? So how is the sine function defined? Can anyone recollect how does the graph look like? I don't have space here. Maybe I will do it here only. How does the graph look like? Can anyone remember? So for example, sin t, if you are taking sin t, let us say in the interval 0 to pi. So it goes something like this, right? So something like this. Now integration in terms of the area, how can you define? Can anyone recollect this definition of integration in terms of the area? It is the integration is nothing but the area under the curve, right? Yeah. So now you see that you have whatever area which comes above, right? So the part which comes above, this part is having positive value, right? And whatever area which comes below this line, this area has a negative value. So when you are considering the area under the curve, this actually, you can see that this nullifies. So whatever, how much ever big interval you take, the area, you see that some part of it is going to get cancelled out. Okay, so you see that because of I have not done the rigorous integration part of this, just giving you the graphical way to visualize this, right? So here you can see that based on the uh, uh, concept of area under the curve, you can see that this integration will definitely exist. Okay, so the next part here, you see that just instead of t, you are now having t minus t by 2. So almost exactly a similar scenario is going to arise for this. Okay, when you're doing the integration, you will arise at a very similar scenario, and you can see that the limit does not exist, and hence you can see that this function also is not in L2. Okay, so like this, each of this example you can understand it individually. So how to check for small L2, how to check for capital L2? Is everything clear? At least so far the examples we have seen. How to check a given function is in small L2 or capital L2? Is it clear for everyone? Please let me know if you understood. Okay, so then let's go with some examples again. So the first one, x and y. So do they belong to small L2 or capital L2 first of all? Does it belong to small L2 or capital L2? Small L2, right? So for small L2, how is the inner product defined? For small L2, how is the inner product defined? The inner product x comma y is defined as x1 y1 plus x2 y2 plus etc. xn yn plus and so on, right? So now this is your x1, x2, x3, and here is your y1, y2, y3, right? So now how to do this inner product? How to do this inner product? So for the first one, inner product of x comma y is x1 y1 plus x2 y2 plus x3 y3, so on, right? So let's substitute the values here. 1 into 1 plus 1 by 2 into 1 by 3 plus 1 by 2 square into 1 by 3 square plus and so on, right? So now what is this? This is nothing but 1 plus 1 by 6 plus 1 by 6 square plus and so on, right? So now what can you tell about this? Do you know how to solve this? Do you know how to solve this? How many of you can solve this? Or can you tell me what is this looking like? There is a name for such series, right? What is it called? So here you can see that this first entry looks like 1 by 6 power 0. This is 1 by 6 power 1. This is 1 by 6 power 2. Right? So this series is actually summation n is equal to 1 to infinity 1 by 6 power n minus 1. Right? So this is a geometric series or not? Yeah, the answer is 6 by 5. So this is a good, very good. So this is a geometric series, and for geometric series, what is the formula to find the sum? A by 1 minus r, right? So a by 1 minus r means, so what is your a here? So this sum S is given by a by 1 minus r. Your a value, the first value is 1, and your r is 1 by 6. So you will have 1 by 1 minus 1 by 6, which is 1 by 5 by 6, so 6 by 5. Okay, is it clear? How did we compute this? Is it clear? Yeah. So similarly, can you do the next one and tell me what is the inner product? First of all, are they are they orthogonal? Are these two vectors orthogonal? They are not orthogonal, right? Orthogonal means you should have inner product x comma y to be 0. And here they are not orthogonal because it is not 0, right? So for orthogonality, you need to check inner product x comma y is 0. Okay, fine. So now try the second problem by yourself. Try doing the second one. So first of all, what is the general term for x here? What is your xn? Can you tell me? So here you see that this is your x1, this is your x2, this is your x3. So what is xn? Xn is 1 by n. Good. What is, yeah, here this is x1, right? So just 1 by n only. Now this is your y1, y2, y3 and so on. So what is your yn? 1 by n plus 1. Good. So this is 1 by n plus 1. Now with this, do the inner product and tell me the answer. So here, what is that you need to do? You have product in the denominator. Whenever you have product in the denominator, how will you do this summation, infinite sum? Can anyone remember? You have to split them as fractions. What is the name called? Partial fractions, right? So first split them as partial fractions and then apply the summation. So first of all, if you split the partial fraction, how are you? What is the value you are getting? You are having now 1 by n is one sequence and 1 by n plus 1 is another sequence. So what is that you will have? You will have inner product x comma y is equal to, now you will have summation, or you will, if you want to write step by step, we can do that also. 1 by n into 1 by n plus 1, or here 1 by 2, 1 by 2 into 1 by 3 plus 1 by 3 into 1 by 4 plus and so on. So this is nothing but summation n is equal to 1 to infinity 1 by n into n plus 1. Now 1 by n into n plus 1 is equal to a by n plus b by n plus 1. I am asking what is your a and what is your b. Find a and b. Now what is your a and b? Have you computed? A is 1 and b is minus 1. Good. So a is 1 and b is minus 1. So what is it you are getting? 1 by n minus 1 by n plus 1. Right? So it means you are having summation n is equal to 1 to infinity 1 by n into n plus 1 is nothing but summation n is equal to 1 to infinity 1 by n minus 1 by n plus 1. Now if you expand this, what is it you are getting? Can you see? 1 minus 1 by 2. This is your first term. And then plus 1 by 2 minus 1 by 3 plus 1 by 3 minus 1 by 4 plus and so on. Now what is it you can see if you take out the brackets? 1 minus 1 by 2 plus 1 by 2 minus 1 by 3 plus 1 by 3, right, and so on. So what's happening here? So after the first term, every other things get paired and they just simply become 0. Each pair they become 0. So what is left for you? What should be the answer? What should be the answer then for this sum? Because all the other sums are becoming 0, right, and infinitely this is going to happen. So what is going to be the answer for this series?
1 minus 1 upon n plus 1.
Okay, but then when you apply again limit n goes to infinity, so what is your answer, final answer? You should not have an n in your final answer, right? So just by visualizing itself, you see that this part and this part, they are becoming 0. So again, you see that the infinite part here also, they will get paired up and become 0. So what is that you are left with? Simply 1. This is a telescoping series, you can see, right? So infinitely, they get cancelled out and become 0. This is a telescoping series. So you will simply have 1 as your answer. Okay. So this answer is simply 1. Right? This is a telescoping series. Right? Okay. Now what about the third one?
Ma'am,
Yes.
but in the last we will left with one pair, na? Maybe one, no, one fraction.
Sorry. What is that you are saying 1 by 4?
Ah, yes, yes.
See, here you have dots. So infinitely this kind of pairing up is going to happen. That is why this is a telescoping series. Infinitely, this kind of cancelling out will keep on happening. After this, the next term is 1 by 4 minus 1 by 5. So that 1 by 4 and this 1 by 4 will get cancelled. Same way it is going to happen repeatedly infinite times. So this is kind of what is called as telescoping series, where infinitely this cancelling out will keep on happening. So what is remaining here is just 1. You understand?
But ma'am, still at the even infinity, there's one term left, na? So not getting it.
What is that one term left?
Like there we left with minus 1 by 4, no? So at last time
Okay, so
there
if
should be
this
one term, no?
concept of telescoping series you are not able to visualize, just look at the nth sum and let n go to infinity. What is the sum of your k terms? So your sum of your k terms is, just take summation n is equal to 1 to k, 1 by n minus 1 by n plus 1. Now what is this sum? 1 minus 1 by 2 plus 1 by 2 minus 1 by 3 up to which term you will have? 1 by k minus 1 by k plus 1. So you will have 1 minus 1 by k plus 1. This is your sk. Is that correct? Yeah.
Yes, ma'am. Yes, ma'am.
Now what is your s? S is nothing but limit k goes to infinity sk, right? Yeah. This k should go to infinity.
Yes, yes, ma'am.
Yes. So this is what I'm referring to as S here, right? Now what is this? This is nothing but 1 is there. So for the first one, limit is not going to affect anything. So 1 will remain, and here you will have limit k goes to infinity, 1 by k plus 1. So now what happens to this term? This is 1 and this is, what is the value of this? What is the limit value of this? It's 0, right? Limit k goes to infinity, 1 by k plus 1 is 0, right? So you see that the answer is 1. Okay, if you are not able to visualize it in this way, this is the usual way to understand. So either way you can
Okay,
understand.
ma'am. Got it, ma'am. Got it. Okay, thank you, ma'am.
Okay, good. Okay, so the next one you see that instead of okay, first of all, this third one, is it small l2 or capital L2? Is it small l2 or capital L2? Capital L2, right? So capital L2 means you have to do integration. So if you are doing integration, what is that you will get? So just one problem at least in capital L2 we will do, and then the remaining you can try and ask if you have doubts in the next session. So here it is t power a and t power b, right? So you have x of t is equal to t power a, and y of t is equal to t power b, and the inner product of x comma y is defined as inner product integral of a to b x of t y of t dt, right? So here what is your x of t? Your x of t is simply t power a, and your y of t is t power b dt. So this you can write as integral of a to b t power a plus b dt. Now this is a very simple integration. So t power a plus b plus 1 by a plus b plus 1. The limits are, is it just a b or, oh, in 0 1, L2 of 0 1. Okay, so here it is 0 1, 0 1, 0 1, 0 1, 0 1. So you will simply have 1 by a plus b plus 1. Okay, so this is the answer. So you try the remaining problems also in the similar way. You have two problems, the same problems actually, and you have the sixth one also. Actually sixth one is already solved by the professor, I guess. So fourth one is also very similar, only this actually they are the same problem only. You just try this yourself Okay, this, take this as a homework, and for this you can refer to the professor's lecture as well. Okay, so try this one and see if you are able to manage. If not, if you have doubts, we can discuss in the next session. Okay, so in today's topic, is everything clear? Yeah. Okay, good. Okay, then see you all in the next session.
Thank you, ma'am.
Yeah, thank you everyone.